almost around embeddings per dB.
Thank you, Spencer, for inviting me for the club, for hosting me, and for the past week of very interesting discussions. So, what is the object that I'm going to talk about? So, I'm going to talk about embedding between various spaces, which I define as we go along. But before we even start talking about that, so all of this will be, so the two different papers that I mentioned as I go along. There's a paper I had is from Borel, which it's not what I was working on. Anyway, but so there's a paper with Borel, which it is about embeddings between different certain dynamical systems where you get rid of certain mindset, and then there will be an expensive, they will get rid of the mindset. And then there will be a problem of capital where which is more probabilistic in nature. Sort of try to describe the go to the top where all of it belongs. But let's start with some puzzles. So these are simple combinatorial problems, simply stated combinatorial problems, which might be of some interest. So suppose I just put this simple set. So by the interval over there, I actually just named all the integer points inside that inside the interval, and so I'm taking the power of that. It's just the neutral grid that we might be thinking about. So I'm taking two element set, and I'm taking a power of that. Looking at the cardinality of this, of course, we are all mathematicians. This is very simple. It's just 3 to the power 2x to the power b. 3 choices for each side. That's about it. Now, suppose I did something different. I fixed some pattern on the boundary. How would things change? Well, things wouldn't change very much. You have now a smaller pattern, a smaller box, and there you can place 3 to the power 2 and minus 1 to the power b dot. Okay, that's very simple. So as a consequence, we see the following thing, that if among all possible patterns, I pick the one with, I want the probability of seeing the one with this nice boundary. Yeah, the one, if I want to see one with this nice boundary which I fix, this will be something of the order 3 to the power minus c n to the power d minus 1. So there will be some term which will be coming from the boundary, which will be boundary effect. And right. So
what do you mean some pattern in boundary?
So just I'm looking. So here when I was looking at the cardinality of these, then I didn't fix what the boundary is. Now we just take the boundary.
What is the boundary?
So you can just take the inner vertex boundary. So take all the vertices. So embed this in ZD and look at all vertices. You have element on the outside, which is neighboring, and element inside, which is neighboring. So that will be so. Right. So this is elementary. So the main question, which it might be difficult to get hold of as we proceed in the talk, is how in general is this phenomena that if I restrict to the boundary, if I restrict to a pattern on the boundary, I don't lose too much. I still essentially lose only as much as the boundary with which is exponentially exceed the boundary. In the audience, yes, so boundary is becoming larger, but it's still small as compared to the volume of the box. So the volume of the box will be of the order n to the power d. The boundary is of the order n to the power d minus 1. And in that sense, the effect is negligible. This is how I like to do it. How, yeah. So, nice combinatorial question. And now let's look at a particular context where this already becomes non-trivial. So earlier I had two symbols and I could place them freely among each other. Now instead I have three symbols. I've been looking at the grid again, but now I don't allow adjacent symbols to be the same. So I'm looking at proper tree coloring. So is the audience familiar with the term entity? Okay. So we will, when it comes to it, I will try to explain more what I mean. So there are certain patterns which allow a lot of things inside. So this is the theorem of Borel, Nishant and Borel, which says the following: that if I take the following boundary pattern, and now I have two colors. Alternative. So I'm allowed three colors, but I only want two colors on the boundary. And alternates. This is orange, but this is these colors. And it turns out that the same phenomena is still true. You have that if you look at colors in this kind of a boundary, and if you look at colorings without any constraints on the boundary at all, you will still have a bound on this side. You will still have a lot of colorings there. But now, there are also boundary conditions which are very bad. So, for instance, let's look at this particular coloring. So there you have, our colors are blue, green, and red. And now, if I look at blue, green, and red over here, it forces this color to be blue. And so, if I take this particular boundary condition, where I do blue, green, and red scientifically, then there's only one way to fill it with the property. So you're saying that certain boundaries are good, certain boundaries are bad. So one needs to be careful when one asks such a question. And I don't know, was any of you in my talk on Monday? Yeah. So on Monday, I spent most of my time talking about this, where how the boundary influences what we see outside. So here we are asking a much clearer question, where all I really want is a nice boundary condition, which would give rise to a lot of feelings inside. A lot of feelings in the sense which I spoke about earlier, that the probability of seeing this nice boundary is only affected by this term, which looks like the boundary size. Okay. So the background will be that you have a much more important training. Yes, so because there are a lot fewer things inside, you can get all possible boundaries when these are quite bad. But right, so there's always some boundary that we can pick, which will be nice in the fashion of I described, which will have a lot of things inside because there will be but then I say nice boundaries, I have more properties. And these are the properties which I have described already. For instance, this coloring, where I use three colors, I can point here. These colorings, it has this nice combinatorial property. But now, if I draw another box over here, and I have the same pattern from there. then I can fill up this gap with some other pattern which will be a property pattern. So if I have a bunch of these, I can extend them to a coloring on the entire object. And which is somewhat important for me. So I agree that there are always line boundaries and there's always bad boundaries if I just care about their estimate. But I want a certain extension property as well from my combinatorial object which I'm trying to look at. So not usually the problem is that I want system with constraints like with the coloring, so that no two adjacent colors are the same. And I want to put some nice additional boundary conditions, which does not have too large enough. And here's okay, so here's a simple question, and here's a simple let's look at a complete model, but I already have no idea how to answer this question. So what we look at is our tilings. So you have a bunch of tiles, P1, P2, P3, which are boxes. So tiles are boxes over here. And now you have this sort of an irreducibility condition or co-primality condition, which says that if I look at the side lengths in a particular direction, they are co-prime to each other. So for instance, if I look at say that I have at least 3 tiles that I'll be tiling with Z5, I would want that if I decide that DCD is equal to 1 and which line this line. Then DCD is that. This assumption is somewhat important in my study. And now what I want to do is compare the following. So the two ways I can tile objects perfectly, which is I take a big enough box and I want to look at a perfect tiling of this box. So this is in some sense specifying that the boundary is completely smooth. And the other is where I don't put this constraint and I allow all possible tiles. And I want to say that so I've written the inequality that we had previously. This one, somewhat technically, where we are trying to, and if you just take the logarithm and you take the limit as n to infinity, it will turn out to be this, which precise, so I want to say that the effect is not with that. And the only real non-trivial case where I know the answer to this is in dimer tiles. So what are dimers? Dimers are simple items. The simplest case of this example is like where your box is this, and then if you are in ZD, then you have maybe D minus 2 more directions. Why about? You just look at boxes like these and you look at tilings by dimers. And now you want to compare the following two quantities. You want to look at tilings which are perfect, and you want to look at tilings which go over the boundary. A perfect tiling is one in which so I have this box. So I can do 2 kinds of tiling. So I can look at tiling like this. So I can look at the tiling like this, which is perfect on the boundary. On the perfect. So, but then I can also allow these tiles to just overlap with to cover the boundary. The perfect are the ones which don't cover the boundary at all. You have a perfectly smooth shape. And in 2 dimensions, this is the capital, and this is non-trivial in higher dimensions, which you can make for Sheffield and Sheffield which sort of it seems It's so we do a lot more than just do this estimate. We understand how the boundary affects the tiling inside. But first of all, it's only in the simple case of diamond tilings. And so far we have no idea about how to understand this question in general. So the reason why I wanted to start with this is, there's a lot of language about, poly spaces and about embeddings and so on and so forth. But the underlying combinatorial estimate that I need is something which probably high school students can understand. And this is what I want to emphasize. This would be interesting even in the 22 can answer the general question.
You could probably say that these dimer tiling, these are perfect matchings of
Yes.
the grid
So
graph.
these diamond
right?
tilings are like, yes. So, yes, but, if I look at the grid. Now, a dimer would have been accounting like this for accounting. This is what dimer tiling. But on the other hand, if I look at what happens at the vertices, then I will get positive factors. Exactly. Sorry, yes. So perfect matching is, if I'm doing the graph, I have a choice of edges such that, each vertex is, belongs to exactly my fit. Okay, so this is the main combinatorial question somewhat here. Okay. So then we can, right. So understanding these questions about how boundary patterns affect what happens inside is an important question in physics. But in ergodic theory, this helps us understand the existence of embeddings from one space to another. So I really like the way how Spencer often explains this, that there are certain spaces in which you know how to solve a certain combinatorial problem. Does this help you solve the combinatorial problem elsewhere? And that's the, if you know that some things have a free coloring, does it give you free coloring elsewhere? This is sort of the underlying theme of the Spencer can perhaps correct me about it. Putting words on it. Okay, so let's discuss the framework we'll be working with. So in case things are unfamiliar with you, please stop me. You don't have to go through 100 slides. Something, yeah, so X is the full space, and you have a Z action from X by homeomorphisms. And by that, we will also mean the PV graph, it's standard generator, so I'm just looking at it. And what we want to understand around from the dynamical system X, such that it is universal. So what does universality mean? Now, universality means that if I take any other system which is free meaning that there are no periodic points, then I can embed it inside the space X. So I have two dynamical systems, and I want to plan to put it on this system, which I want to do with the system X. And I want to understand when do I have enough freedom such that I can embed any other system which is reasonable. This reasonable, what is reasonable comes from this entity and from this premise inside X. So we'll be talking mostly about coloring as an example. there are many other systems to which these theorems apply. And we'll be looking at. So a related question regarding the chromatic number, which would be familiar to the project. So what is the chromatic number of a graph? It's the minimum number of colors that we need to color a certain graph. So if I'm looking at the chromatic number of the grid that we are talking about, here that is a relationship with skill, right? You can alternate between say green and blue, and you can color the entire.
There's renegade red. There's a renegade red.
Yes, it's just to remind the audience that we indeed are talking about two colors. Yes. Every time I give this for somebody else, I still haven't. So when I have ZP acting on a Borel space in a free manner, then the way I think of this action is that my space sort of decomposing into uncountably many properties of it. Now, this is not a very good picture to have in mind because it's not true that say the point which I'm mapping to the origin by looking at this decomposition, I can sort of string them all together in a Borel manner. But I cannot do. But then nevertheless, it does give you an actual Borel graph structure on the space. And the question that we want to ask is, what is the chromatic number of this action? How does this relate to the question of embeddings is something I will come about eventually. So, but there is a relationship between them. If you can, the way you think about it, basically, for instance, if the chromatic number is 3, this would mean that you can map immediately from your polar space X into the space of property current. So you need not be 1-to-1. Now, if your map is 1-to-1, then in fact it's an embedding.
Interesting. You are in a group of people which ignores the classical number, classical. But although this group of people,
Yes.
the relevant data,
Yes.
good ignorance and they not in detail.
The one for
Because the commanded number is 2 of them.
yes, yes.
You something like.
For me, yes, it is something else. So, right, so, and this is probably also emphasizing the fact that, and when I have a ZD action on a polar space, I'm not just decomposing the space into uncountably many copies of Z2 or ZD, because then the chromatic number will just be 2. But what we want is we want to break the space into these. If I want to take coloring, then I would like to break the space into 8 different parts, such that if a point belongs to one of these parts, then and if I apply the action on the okay, so I say neighbors of X over here. By that I mean if I apply say one of the unit vectors on this point, then it will belong to the complement. This is just saying that the colors adjacent colors are distinct. And here's a quick argument to say why it is not using it. It will be some periodic query, which I need now. I could have avoided it, but it's a lot simpler in that sense. So suppose I have an action bar happening in morphisms, and suppose there are 2 colors. So this will mean that I can decompose the space into 2 parts. The first part will be one which will be mapped to the first color, the second part will be mapped to the second color. So this would mean in the language which I described earlier that if I have a point in the first part, then by any of the unit vectors, I'll be mapped to the second part and vice versa. So What this would mean is that if there is an invariant probability measure on the space, if there is a probability measure observed by the space, then both of them will have the same probability, both x1 and x2 will have the same probability. And if I, instead of looking at the map P, I looked at each square, where I applied in that twice, then it would be that invariant. So this will mean something about the action. It would mean that your action decomposes in a particular bit. And most interesting actions don't decompose in that particular way. So this is something which I'll tell you from robotic theory. So usually, even if I put a probability measure on the space, you will not equal to 2. So now Jackson asked what is the chromatic number of a free Polish action of Z. So they actually were interested in the free partnership and a particular action. And then simply selecting and I was also given I could have asked answer before I close this up.
And also celestials. Because people not make the polytech selected.
So that the chromatic number between 2 and 3 plus 1. So these people was essentially what kicked off the whole study of Borel fundamentals, where we try to study the chromatic number of certain Borel graphs. And so the chromatic number, so I am using the periodic points and I'm keeping them separate. They, of course, I can but they cared about the periodic points as well. And they showed that the chromatic number is exactly between 2 and 2D.
Very correct. 2 is 2.
So 2 is still a possibility because you can have a very stupid action.
I mean for a month.
Yeah. So
But I think that you knew it.
right. You were looking at a particular action. Yes.
You knew the fact that it's for 2 years.
So right. And so then the question now so that in this particular context, it's actually where I'm looking at 2 actions between 2 and 4. And the chromatic, it turns out so this is and it was also announced by Borel and so that the chromatic number of Zelda action molecules is either towards 3. So we could the number. So proof is fairly general and it applies to a large number of examples and questions which were raised by dog accident 0. And what I'm going to do is usually, not suggested in a talk, but I'll actually try to tell you what the proof is like. I'll give you a flavor. Okay. So let's try to sketch the proof. So maybe before I sketch the proof, let me, since I've already given you the picture, let me talk about how we somewhat know about it. Okay, you will see more picture as we go along. But the tendency of the about it is we try to divide the space into boxes. Now these boxes are very large. And I divide them into boxes. And now on each box, the chromatic number is actually 2. So it's very nice. So I can color these boxes very easily. Now, then these bigger boxes on which I want to extend this box color. And now it becomes interesting, and I need this extension box. So this is what I will describe. So how do we get these boxes? So there's a result by Rockman which was extended to Z by magnitude and that. And in fact, it extends to all available groups. That there exists some that suppose I fix a reaction and I take some n. N is like the size of the box. Epsilon is the error. So it's the proportion of space which I leave outside the box. So the space element. Then there exists some measurable set A contained in X such that if I look at translates of that set along the box, I'll always get something disjoint. And the rest of the space has very small measure, has measure less than X. So what this box means, since I'm looking at one empty party, it means that this corner and these corner elements belong to the set A. And this means that if I see an element of A here, when I move see another element of A in the box, then this was the joint between, and the proportion being less than epsilon is saying that the measure is small. So in some sense, I have divided the space into these boxes, and now the question is how can I color the space using this? So what I do is, so B is this box over here. And in all these boxes, I can now put colors as I want. Right? There's no constraint. Now, the problem is that some of these colors might crash on the boundary. So I would probably take slightly smaller boxes and color those because I don't want crashing down. But there's a bigger problem that even though I color these boxes, suppose I pick the color on the back, which is now using all three colors, red, green, blue, red, green, red, green, blue. And I take a similar coloring on the right hand box, which is red, blue, green, red, blue, green, red, blue, green. Then there's no coloring in between which will produce together. So the way I think of it is that the colors are on one side. And so now we have three colors, orange, then red. And as you are walking on that line down here, you're cycling in one way. This means that if you take any line which is close to that line, then it will be essentially cycling in the same way. If you have two lines where one you are cycling in this way and the other you are cycling in the other way, you won't be able to come together. The topological picture is very important. It relates to the existence of a certain height function, which makes this model of three colorings somewhat so this tells us that we probably need to restrict to nice colorings where you use only two colors, and this is what I specified earlier. So these are like the boundary of the boxes which I was talking about. And so check about and if I have these two colorings, then I can always fill the gap in. But now I will use three colorings because I will need to take the sanity issue. Okay. So what do we have? We have these boxes, and I have colored all these boxes appropriately. But now there is a lot of empty space which is left over here. Right? So what do we do? Well, we take even bigger boxes. So forget about the writing on the right one. We can talk about it. Right. So I have these. I'll take a bigger box. So Laughlin's lemma allows me to do it for every epsilon and every n. So now I take a much larger n and a much smaller epsilon, and I'll cover more portion of the space. And now the only problem here is that it will hit the other boxes which I had before me. But that's not really a problem if you what you do is you erase the colors on the boundary. Now, this is what we discussed earlier, that the boundary is not smaller than the volume of the box. So the things that I erase will be a lot fewer than the things which I actually put in color. So, and if I continue this number, using some probability, I will eventually get a coloring of entire space. So, there is some sort of iterative coloring where I take certain boxes, I color them, then I take bigger boxes and I erase the things on the boundary, I recolor them the inside. And I keep on doing this for bigger and bigger boxes. Eventually, I cover the entire space. There's some probability which is working in the background, but you can safely ignore that.
And some also, some sort of convergence.
Yes.
At some point, the convergence.
Yes, yes. And this is that's an excellent point. And for this, or where do I change my color? I change the color if I belong to the boundary of a box. So all I need is that I belong to a boundary of some box finitely many times, which is an extremely important point. And yes, so this can be controlled using probabilities, using Borel campaign that I have worked with. But let's keep this comment in mind for a few more minutes. That the problem is that I don't want to change the color infinitely many times. I only want to change it finitely many times. There's a very useful perspective to have.
So that's so
Yes,
it seems to me that the children have a mindset really good that they do.
absolutely.
Oh,
Yes, 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 yes. Another excellent point. So yes, so there's a null set which will be left, which I haven't colored, and this coming from the this. So full set is one in which is outside, which has measure zero for all ingredient probability measures. And this was already known to its
Measure one.
the-
Full with measure one.
did I say measure zero?
Yeah.
Sorry. So a full set is full, not empty.
I'm trying to read.
Yes.
I can see
Okay.
the motivation to see and to committing things. Yeah. Okay. Don't get me started back. So, I think that is one which has never one of all in probability measures. And as it was pointed out, indeed, that construction will go on a full set. This is beyond that. So Simon and Robinson didn't exactly do this, but they asked, this was a null set with respect to a given probability level, which is also what R has done. But it's not such a big deal to take care of this. So here there is a very interesting question. So what I did is I made a proper tree coloring of full set. Now the question is, so I create my abstract length in space into this nice combinatorial of the principal tree colors. Question, can I recover back my original system from this coloring? In particular, is the coloring and embedding? So this was the question that we asked, and the answer is yes. So the entropy is some measure of the size of the space, which roughly says, which tells you, for instance, what can, like it gives you an obvious obstruction to what can be embedded in there. If something has smaller, something has big entropy, if X has big entropy and Y has small entropy, then you cannot embed X and Y. This is for the purpose of this talk, this is how I want you to remember. Now, there's another notion of entity, which is the topological entity, which talks about, if I'm looking at say the coloring, what are the total number of the colorings on the box? And now you take the limit of the box to infinity, look at the growth rate, that's the entity. When I'm looking at timings, I will look at all possible timings of the box. Mind you that I'm not saying perfect timings or anything of that sort, just timing. So my tiles are allowed to cross over one. So I look at the growth rate on that, that would be the entity of the time. And this is what I will say. And what I am now going to prove is that the space of coupled P colorings indeed is universal in the sense that I can embed everything else which has smaller entropy. And the thing which is involved, which I want you to remember, is precisely this combinatorial estimate which I spoke about. So in words of body theory, we say that the proper coloring is almost universal, almost because of the number of possibilities to not get rid of the answer in the statement. Indeed, right. So the question which remains, which is not addressed and which is open, is the following: is to prove that the space of proper three colorings is universal. That means that there is no need to get rid of the null set to obtain an embedding. And this remains open up until now. My people Spencer also do not address this question. But the one point here is that we want the embedding. This is what this is. So our techniques apply to a large class of examples. I'm just going to mention a few of them. So, coloring is a graph homomorphism. Has anyone heard of a graph homomorphism here? Is a graph homomorphism? If not, it will take me 1 minute to describe it and it will be sure. And we have a lot. Give it back. So the space of graph homomorphisms has this property. Space of domino timing has this property. The space of rectangular tiles has this property, but we can't get this number h to be the entity of the tiles. So since we already know this picture, what is this number h that we can see? So, let's talk about the doctrine of the just to remind us that actually we are finding in different class. And now I'm going to look at about another thing from I didn't say you So the things of three colors is if I'm looking at a map from any graph, this suppose that one of these vertices is equal to one. Now, the distance is equal to one or two and three. So, these we will have to either to and then we can get property color. Now, in the description of the space, I should tell you what the topology of this, like when we say space, we probably mean some topology. So this is contained in, so if this is the space of the matrix, it is contained in this. Of course, here I'm using a slight, slight and actually both the graph and the set of vertices. Sorry about that. Now, this is a nice technological structure. This is you can put the discrete topology on a finite set, which makes it compact. And then you take the product topology and this gives the compact space. And this is a closed subspace of this, which is compact.
It's interesting that you put here. You forgot your not, you go to say find non-bipartite. Why do you choose non-bipartite?
Non-bipartite is because
You expect that you expect to have
right. So the reason why it is better, so this theorem of universality or theorem of embedding is only true for non-bipartite tasks because of the parity issue. So if you have say a bipartite task, then you would have a set of say even with two partite classes, and this would mean that you have some periodicity in the system which you are embedding. Or
you don't want this, you don't want to
I should be this could hold for all possible systems. So if you
you're expecting this to be universal.
yes, exactly. Again, yes, exactly.
And it's not enough to old site. Old site.
It is enough. It is enough. So this is true for any non-bipartite graph. So if you have any odd cycle, then your graph is not bipartite and it will be there. So is the topology on the space here? So now, what I want to do is the following. So I want to first look at the topological entity of timings by this can also be given a very nice topology, which the center of the tiles will be like 1, the rest is like 0, and this will form a nice square side. So this is so tau is the set of time. It will be rectangular tile with a nice condition. It will be this event where the number of tiles. So this is the topological entity, and so these are not necessarily for some of these tiles might walk over the boundary. And the H in this theorem, which are the kind of systems which I can embed, is given by saying now I'm doing number of functions. One and so if these two numbers are the same, I have universality. And this is the main problem because it was kind of pretty much,
Which makes me so.
okay.
And if they're not the same, you are not.
If they're not the same, no, I cannot say that it's not universal, but then I will be very surprised with the test. But there's no, it's not an intermediate. So our techniques are fairly general. They apply to a large class of examples, like you said. And they build upon techniques that were developed by my possible, which was a wonderful solution. And it also covers examples which are not covering the entire list, but general topological dynamics. And Simon and Robinson proved universality for certain light systems, which not covered above. And from the stream of domino patterns, we estimate the spoken about. So now, as it has been pointed out before, there is a significant problem with trying to get rid of this almost part. So everything is defined when there's a probability measure and you're looking at a null set, or you're looking at something which is universally null, which don't carry any probability measure. So what we needed in this, and this was pointed out, that I would do this erasure on the boundary, erasure on the boundary, where I remove things on the boundary. Now, if I erase them enough, enough number of these, then everything makes sense. But there I'm making some assumptions of the sets A, which I'm taking as a base of what we should look at. So this no longer holds in the general Lewis setting. So this was proved by Gauss maximum that okay, so there's some technical assumptions over there, but for you, you could just think of this as some compact, nice compact dynamical system. And now suppose you are given a set of Borel sets with the following property. That it is a complete section in the sense that it cuts to each orbit. Okay, so there is more complicated. So what was the basis of my construction? I had the towers, right? These were rectangles. So I took my space and I made bigger and bigger rectangles of squares in my space. Now, this theorem, forget about the technical assumptions above. This theorem essentially tells you that if you try to make such construction in the Polish setting, when you're not allowed to throw away a net set, then you will fall on the boundary infinitely many times on a very large set. So when I'm looking at probability measure, then I'm somehow throwing away a very large part of the space. And so even though on this diagram, if you look at this diagram over here, it seems that the boundary is rather small, but this is not in the Polish setting. This somehow is too large. In fact, it intersects infinitely many times. So what this would mean is that what does it mean for this to fall infinitely many times? Every time it falls on a boundary, I change the color of it. So now if it falls infinitely many times, I'm changing the color infinitely many times for a particular point. This means that I'm not converging to anything. And this is why it's very important that this set the that I don't think it's okay. So
This color with this band set is very large in the
Right. In the middle theoretic sense, it's small, but it's. And so Gauss-Jackson and Seward love this. By the way, a few of this theorem can also be found in paper, which is so Gauss-Jackson will have many more technical assumptions than the guidelines and theorem are from multiple theorems are somewhat straightforward proof, but you need to know some dynamics. That's not I guess not too much is always a function of what you are looking at. So, but I really generally think no. Okay. So they also suggested workaround, and the proof of this can be found in a paper by Alguna and Spencer. And the workaround or a walkaround, what you want to say is, once you see it, it seems like a very simple idea, but it took some time to actually come about this idea. And what you do is the following simple thing. So your box that you can start with, intersecting a lot of other boxes, you just walk around them. And whenever you intersect the box, you just include the box in your set. And you kind of construct using thousands of different workers. So this does not seem like a very non-trivial idea. But now notice what we have to do. Now I have some key coloring or some tiling of this very strange set, which I want to extend. Provided I have actually squares or cubes or something like this, extension was a somewhat of a trivial problem. But now I have a much more complicated something which looks like a fractal more or less. And I want to decide when these can be extended beyond the set. And this is a lot of my paper expensive. So as I said, this can be very complicated, and this can be so complicated that by throwing away the special zeros set, I could find embeddings, not just maps into three colorings, they would be injected. I can no longer do it in this setting. I have no idea how to get embeddings, and that is why embeddings through the space of three colorings really not allowed the system to come into question. Any nice system, where there's no exchange between the system, I'll probably be able to take your tools and be able to do it. But I'm not sure. I'm not being seen as you have to do, but so nevertheless, we were able to use this to bring the correct bound, to mean what we said. The coordinate number was already with the system and angle of 2 or 3. Again, on the case of general, they apply to a lot of different things. It applies to timings. It applies to these connected by infinite Hamiltonian paths. So paper answers some questions with Gauss-Jackson and Seward, and extended some other results which are presented. So in presence of an ergodic measure, the second result of a directed by infinite Hamiltonian path is had been announced by Dominovich, Prabha and Zhang. There's somewhat important in ergodic theory, but you have a complicated ZB action. Okay, but I could probably tell you what a bi-infinite Hamiltonian path is first. It's this. So you have a graph. A Hamiltonian path is a path which meets all the points in the graph exactly once. And a bi-infinite complement path is exactly what you would imagine. It's some sort of snake which is going around the ZD lattice, visiting each vertex of ZD exactly once. And it's now intuitive that these things exist, but not only that they exist. Okay, it's not a non-intuitive that they exist. So if you probably sit down with a piece of paper, you'll be able to figure out quite soon. And that, in fact, you can actually do this in a Borel manner. So you can do this even when you don't throw anything away. And what this tells me about it is the problem that if I have any ZB action, then I have a very nice Z system which gives me the same orbit structure. So if I had the ZB action, and if I look at a particular generator, it would move me along the coordinates. Now, if I have a Z action, it would move me along these diagonal Hamiltonian path. So, and in fact, it's okay. So now the thing is the following. So I have this picture where what would be intervention. So I have this picture where you have boxes, and now in all of these boxes you have some portion of the bi-infinite Hamiltonian path. And now you take a big box, and you want to extend the bi-infinite Hamiltonian paths to this bigger box. This is already a very complicated question. Not very complicated, but somewhat complicated. But now you want to do it when your boxes are not boxes, but these with these very strange pattern like one. And so this becomes technical. There's something to do here, not very, yeah. A lot of wasted paper. So now the question which may ask is, okay, in the Borel setting, I mean, so that it's still open, like you can know that it's still open that whether embeddings exist without going away in that sense. Then I get the Borel embedding to entire space. So there are two big things in this direction which I would like to point out. One is by where what Anish indicates so what Anish would translate to in our context, it would give us convergence into the space of critical symbols without any constraint. And there are some assumptions on what kind of things can be embedded. So here I see the theorem as it is, but if, as a corollary, you would get a certain kind of universality for the space with the how can we do this space universality result? Where he coded for all, say, set of symbols without any constraint. So forget about the relationship for final type. Suppose you have two colors and you have no constraint on how they're placed magnets to each other. You can embed any action which is free without doing anything at it.
What's the reason for assuming that the system is not
Right. So the way this is proceeding with the following, we know how to deal with the part which has created problems. So now I give it backwards and then of course, this is not the end of the argument because maybe the matches that we got they intersect each other. So there's something additional that we need to do in this work.
This is simply a case of it.
This is simply a case, but it's the important case. Once you do this and you deal with the probability part, you put them together and there's an argument, relatively tough argument, which will give you the entire. So in the meantime, what we could do is we could prove some intermediate results. which is the following. So what is a shift space? A shift space is simply something which is a compact invariant subset of symbols, finite number of symbols to the power by t. So these are very special Polish actions. So if the entropy constraints are satisfied, then you can actually embed the free part of that space into the space of proper free context. So from here to prove that the space of three coloring is universal, all you need is lots of examples of universal shift spaces, and that will be enough for. And there are candidates and their claims. So the claims are this might be. Again, this can be generalized designs, this can be different parts. There are homomorphisms. This all you need is this extension property. And this our method is far simpler than anything else which is around, but it's restricted to the level spaces. So one of the questions which one may ask is that all our results are Borel. And part of the reason why I'm doing it right now is what we wanted to talk about is whether we can make these maps continuous. And this again turns out to there's a nice paper by Carl Maxson which deals with this continuous combinatorics. Now you know that certain things can be done in a Borel manner. Can we do them in a continuous manner? For example, this map from your arbitrary polar space to the targets can be doing continuous. Now, of course, from an arbitrary space, there's no way that one can do it because of topology. The space actually demands that heat. This is the homomorphic to a campus. So this is going to be a zero-dimensional space. So unless you are trying to embed something which is zero-dimensional, there's nothing. But are there any further constraints? With all these things being continuous, and there is a difference. So it turns out that there are spaces for which a four coloring exists, but a three coloring does not exist. This goes back to the paper of Brown and Jackson. And the argument there is somewhat of the following kind. Four colorings are very nice as compared to three colorings. So here's a nice puzzle if you got board in the top. Take these slabs and now take any four coloring on this slab and any four coloring on this slab. You can always put them together provided the width is bigger than 3. And this can be displayed in all dimensions with your colors. And I already told you that there are certain three colorings which can be put together. And this is what lies in the class again. The other subtlety is given a sorrow to prove the following that there's no continuous embedding of the space of proper three colorings into the initial shift. So the initial shift is where you go from constraints. So if a common result in my document, it follows that there is a Borel isomorphism between the two spaces. But continuous, we don't know. So understanding the continuous combinatorics is definitely the next thing on our list, and from various perspectives. So one of the questions which are raised in probability often is that suppose you have some sort of randomness, can you somehow code it to get another proof of to get some system which is more useful for their current application? And For this, we need maps which are continuous up and down. And so it's a very interesting question, which we don't address, we have a question now. And this is the open question which I posed earlier. I will be very happy if somebody has an idea. And so this is assuming which is coming from an imperfect timing, we can always extend to a perfect timing. It was something which I did not talk about, but this is also quite perfect. For other questions.
There's some additional questions. So the three parallels that you did this guidance.
Yes. And so, for three coloring, this walk around does not pose a bit few problems. So essentially, you have a three coloring of these practically shapes, and you just need to extend them to hand. And there's some very general idea about how it can be done. Yeah, so it's cool when your system, which you're trying to embed or factor has something that is, and then it is split. Otherwise, it's
Question also is think about the continuous.
yes.
In the continuous, you are willing to compromise on the topology. What about going to have nested? The space of the dimension. The compact metric and capital dimensions. So if you are willing to compromise and solving the questions in every meter, yes, then there's no difference because that space is equal to any other space more than a meter.
Sure. In general, you have to be size. Your versus a mean of your size. I'm thinking about being down. Maybe be time that I will put it on the left. And the left block inside. And the exercise. And then I think we even about the times. Not much larger.
Any other questions? Thank you very much.